So let's do one more electron configuration. So we have zinc. We're going to put our finger on zinc on the periodic table and then read across the periodic table, take into account each electron. So the first row, 1s2, the second row, 2s2, and then we have all those p electrons on the second energy level. Then 3s2, 3p6, 4s2, and remember after 4s2, then the atom is big enough that it can put more electrons in the d energy level. So 3d, and there's 10 of them. Recall for the noble gas configuration, electron configuration, you're going to go back to the last noble gas, and the last noble gas for zinc would be argon. So zinc has everything argon has, plus 4s2, 3d10. So this right here is argon. These are the core electrons, the ones that are closest to the nucleus, and these right here are the outer electrons or our valence electrons. So when we write an electron configuration, like I've been teaching you, this is a ground state electron configuration, or the lowest state that it can be in. Let's look at sodium's ground state electron configuration. So 1s2, 2s2, 2p6, 3s1. And then these are two excited electron configurations. First of all, we can tell it's sodium because we can add up all the electrons by adding the superscripts. So and there are 11 electrons, so that is sodium. And it's the same thing for this one. What we see here in this first excited electron configuration, we see that there's an electron that's missing here and it's gone up to here. So either they've written it incorrectly or it's called an excited electron configuration. So you would be expected, if you were given this excited electron configuration, to write it in the ground state. And you would just write it like this. So just write it as normal, count how many electrons there are, so what you know what element it is, and then write it as normal. That's your ground state. On this one, we see that my 3s1, it has gone to a 4s1, so that excited electron has gone a little bit further away from the nucleus, and so again, you can tell this is sodium because there's 11 electrons, and you would, again, just write the normal electron configuration as above. You also could write the abbreviated electron configuration. That is always accepted. So sodium has everything neon has plus 3s1. So that would also be accepted. Orbital diagrams are another way to express what those electrons are doing, and this one shows the electrons in the orbital. The orbitals are represented by little boxes and they are labeled. So in my first example right here, you can see there's a box for each orbital and that they're labeled with the sublevel, so the 1s or the 2s. The electrons are represented as arrows. The very first electron to go into the orbital is always an up arrow. You can stylize it and have it a little halvesy, or you can do a full arrow. It's whatever you prefer. Also, the orbitals do not have to be boxes. You can use parentheses. You can use circles. You can even just use a line. But what is important is that you label it. So I would label this is a 1s. And for lithium, you would put in 3 electrons total. So you can see that right here, they did an up arrow, then a down arrow. That's the 1s, and then they only had 1 electron in the 2s orbital, so it's just represented as an up arrow. Let's go through each one of these electron configurations and just put it with the orbital diagram. So again, on that first one, lithium, it has 3 electrons. I'm going to write the electron configuration to help me out. So I'm going to have a 1s sublevel and a 2s sublevel. In my 1s sublevel, I have 2 electrons, so an up and then a down. And then in my 2s, I just have an up. In beryllium, there's 4, so that I have 2 orbitals that are completely filled. In boron, I would write out that I have my 1s, my 2s, and then when you look on the periodic table, there are 6 p electrons in the p block. There are 2 electrons per orbital, So if I take those 6 electrons that can be in the p block and divide by 2, I know that I need to have 3 p orbitals for anytime I have a p. And I just put my 5 electrons from boron into the orbital, and we go up, down. So there's my 2, and then my 2s, up, down. There's my 2 and the 2s. And then in my 2p, I only have 1 arrow. And it is important that you draw those empty orbitals. So I would just show that there's 1 electron in the first orbital of 2p, and then the other 2 are empty. All right, let's go to the next one. We have carbon. So carbon, we have our 1s, we have our 2s, and we have our 3 2p's. And then when I go to put the electrons in, it's just like boron above. So up, down, and then this is important. I have 2 electrons in the 2p, but they spread out. So this is known as Hund's rule or the bus rule. So every electron gets its own orbital unless it's forced to share. And because I have lots of room, there are 3 p orbitals. I can spread things out, so I don't have to scrunch them all in one orbital. Notice that they're both up arrows. The first arrow in an orbital is always an up, and again it spreads out. So you're going to see the same thing has a 2p3 as part of its electron configuration, and so that just means that you're going to have 1 arrow or 1 electron in each orbital. When you get down to oxygen, oxygen has a 2p4 as part of its electron configuration, and so how you would put that into the configuration, and I'm just going to do just the 2p. You're going to go up, 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 and then go back and put in 1 more electron in that first orbital. So, and then we come all the way down to neon. So neon, everything's filled in. So if you have a P or a D or an F, the electrons are always filled in this way. They spread out. You put all the up arrows in and all the P's or the D's and the F's, and then you would put the down arrows in. So again, that's known as Hund's rule or the bus rule, meaning when you get on a bus, everybody gets their own seat until all the seats are filled, and then you have to start sharing. So let's just practice doing these orbital diagrams. And remember, there's 2 electrons per orbital, and you can do whatever style you want, but always start out with your electron configuration. So boron does have 5 electrons. So 1s2, 2s, 2, 2p1. And then you are going to label each of these orbitals. That is very important. And have a little bit of space between the 2. And then you're going to put your arrows in. Again, you can do full arrows or the little halvesies. It's whatever you prefer. All of it is accepted. When I come to the 2p, it's just going to look like that. So there's my 5 electrons in boron. Let's go ahead and do iron. So I'm going to write out the electron configuration first. And I'm going to use the abbreviated configuration. So for iron, that means I go back to argon. That's the previous noble gas. So iron has everything that argon has plus 4s2, 3d6. So for this, I'm just going to write out just the ones on the end. So 4s here, and then 3d. So when you look at the D block has 10 electrons across on the periodic table. So since 2 electrons can go in an orbital, if I have 10 electrons, that must mean I have 5 orbitals. So I'm just going to write these out. 1, 2, 3, 4, 5, and then I'm going to label them 3D. And let's put in our electrons. So I have up, down, so there's my 4s2, and then 3d6. I need to put in 6 electrons. So remember, they spread out. Up, 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 and then I have 1 more down. So it goes in that first orbital. So this leaves iron with a lot of unpaired electrons right there in its d orbital. And why this is important is our next concept. So paramagnetic and diamagnetic. In paramagnetic, that means there's unpaired electrons. That means in the presence of a magnetic field, there will be some attraction to that magnetic field. So one of my students came up with this saying, pair me up with an electron. So these are the ones that are attracted to a magnet. And if we look at oxygen, and let me just draw just the end. So this is the 2p. We see that there's 4 electrons, so up, 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 and then down. You can see that there are 2 unpaired electrons. This is going to make it attracted to a magnetic field. And I do have a video that shows this, and I will link that right after this instructional video. What is diamagnetic? So this is the one that's not attracted to a magnetic field because all their orbitals are filled. And I'm just going to do the last one, and I see that it is completely filled. So this is diamagnetic, and again, one of my students said they remembered it this way. I would rather die than be in a magnetic field, so it is not going to be attracted to a magnet or a magnetic field. So we can practice figuring out if something is paramagnetic or diamagnetic. So first find the electron configuration, draw your orbital diagram. Usually just the last one can show you if it's all paired up or if it's not paired up. And then if it is all paired up, then it would be diamagnetic, and if it wasn't, then it would be paramagnetic. So let's do chlorine. So this is chlorine. The electron configuration is there, so it ends in 3p5. So I'm just going to draw out the 3p5. Remember, p's, they have 3 orbitals because on the periodic table there's a block of 6, so 6 divided by 2, I'm going to have 3 orbitals. Let me put in those electrons, so up, 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 down, down, and I see that there is one that is not paired up. So that means that this is paramagnetic. All right, let's look at zinc. So zinc, write the electron configuration. So we have, so whatever zinc has, whatever argon has, 4s2, 3d10. We're just going to look at the very end part. So here's our 4s, and that's filled. And we look at our d's, so 5 orbitals, and they're completely filled in. So they're completely filled in, so it would rather die than be in a magnetic field. It is not attracted to a magnetic field.